Morning, everybody. Can you hear me? I'm having trouble hearing. Can somebody tell me if they hear me, please?
Yes.
Thank you very much. Appreciate that. Good. All right. Make sure everything's connected up here properly. There we go. That's better. All right. Well, let's get started here. Okay, just a reminder, I'd like everybody to have their video on during the meeting, please. And if you can't have your video on, then you need to send me an email saying why you can't have your video on. And we'll see what we can do to work it out. Some of you have already discussed that with me, so we'll take that as it comes. All right. So we were looking last time at questions 1 and 2 on the test. Somebody's going to need to mute. I'm not sure who it is. Okay, so now we're going to look at the next thing in the notes here, which is the relationship between rate constant and temperature. Now there's a quiz here. This is not actually on the test, but there is a fun quiz about it, and you can get some information on how to do that fun quiz from this section of the notes that I'm showing you here. And it's a link between activation energy and K, the rate constant. So what you'll see here is this diagram. It's a reaction energy diagram. Starts out reactants, goes to products down here. And you can see that this is energy on the y-axis, and this is the pathway of reaction on the x-axis. So we're looking at going from reactants to products and the energy changes that occur during that process. And the activation energy is here. I'm talking about this because you actually do this in the lab, but we don't do it in the class. So this is another resource you can look at to understand activation energy in relation to what you have to find in the lab as well. But you can see here it's the hump. It's the energy required to actually make the reaction go, to actually turn the reactants into the products. If you don't put enough energy in, then the reaction stays as reactants. It doesn't move into the products at all. But there is a link here between the rate constant and the activation energy, which is EA. And that's this one here. And if you have the correct data, and this is what you'll do in the lab, you'll have temperature and you'll have K. And if you take this Arrhenius equation here, and then we take the natural log of everything there, we end up with something that has the form of a line y equals mx plus b. And then we can determine the EA over R, which we can get from the slope of this graph here, which is 1 over t versus natural log of k. So once we do that, we can get the slope, and then we can calculate the activation energy. So that's all that this is about here. You can have some fun with the quiz. It's extra credit, but there's nothing on the test about this. And if you're having trouble with anything on the lab, you can come back, you can take a look at this stuff on the PowerPoint slide. Does anybody have any questions so far? Okay. All right, so I'm not going to go really into anything about that since it's not on the test here. So let's look at applications of reaction orders. So we've been talking about rate equations. Now I'm going to show you how rate equations can be applied to actually figuring out what's going on during a chemical reaction. Now I want you to be, when I go through this, it's going to seem difficult at first, but I think once you see where I'm going with it, you'll be able to understand a little bit better. It'll give you a little bit of context as to why rate equations are important to us and how we can use them to figure out what's going on in a reaction process. So here is an example here. It's an SN2 reaction. Don't worry about what SN2 is, but it is a certain kind of chemical reaction. The C4H9Br is this creature here. And each of these represents a carbon, and there's hydrogens on each of these, just not drawn in. So this whole thing is C4H9Br, and we got a reaction here with Cn minus. Now, by experiment, it was figured out that the rate equation is K, C4H9Br, and Cn minus. What that means is the rate depends upon the C4H9Br and the Cn minus. So it depends on both of these reactants. Now, when I say that this was found by experiment, what I mean is a bunch of experiments were done very similar to what we did last time. We talked about different concentrations and then finding the initial rates and then comparing the initial rates and getting the reaction orders. We did those kinds of experiments, and this is the rate equation. This is a rate equation we came up with, that it depends on both of the reactants. So because we know it depends on both of these reactants, then we might be able to come up with a mechanism or a way that this reaction is probably proceeding. And we would choose a reaction that involved, or a mechanism that involved, both the Cn minus and the Br, the C4H9Br compound. And this might be a way that we would interpret that data. So because both of them are involved, we can say, well, Cn minus attacks the C with the Br, and we end up getting this as a product. Now, you won't have to do any of this kind of stuff on the test. So don't worry about that. I'm just telling you what this data tells us about what's going on in the reaction. There is another kind of reaction that I want you to compare this with, and that's called an SN1 reaction. It's a similar reaction. You'll notice, though, that the structure here has changed a bit. And because of that, the rate is now KC4H9Br. So what's really important here, and this is the only thing I really want you to get from this, is that the rate does not depend at all on the Cn minus. So it only depends on the C4H9Br and not the Cn minus. And again, this is found by experiment. We find that no matter what concentration of Cn minus we have, it doesn't change the rate. So what's the implication of that? Well, the implication is that it must be more than one step, whereas this one up here was just one step process. This is a multi-step process, or at least a two-step process. The other thing we know is that the rate only depends on the C4H9Br concentration, which means that that's the only thing that's involved in what we're calling the slow step. So if we've got a multi-step process, and we know we do because there's no mention of Cn minus here in the rate equation, so the Cn minus must be coming in some other step. So we know that if there's two steps, one has to be slower than the other. One has to be slow, one has to be fast. And whatever's slow, see, the rate depends only on the C4H9Br. The rate depends on the slow step. So this might be the mechanism we'd come up with for this reaction based upon this rate equation data that I'm showing you over here. So I don't want you to go into this too much. I'm just telling you that this is just because of these different rate equations, we can come up with different mechanisms for how this is going depending on what we're seeing in the rate equation. And the only thing I really want you to understand is that if something's in the rate equation, it means that the rate depends upon it. And if something's not in the rate equation, it means that the rate doesn't depend on it. And if it's not in the rate equation, it's because it's involved in some sort of faster step down the line. I'll give you a little bit of an example here just to show you what I mean by fast and slow steps. So I want to give you an example. Let's say we've got a road here. It's not a very straight road. But then there's kind of like a bottleneck because there's an accident or something here, and you got all this traffic here. And then it can go out again to a 4-lane road or whatever you want here. But traffic can only go through this lane here. So we've all been in this kind of situation. I know we have, when we've been traveling along the road and there's been some sort of obstruction and everybody's had to get into one lane in order to get through. I call this a bottleneck. So if you're going from A to B here, your time to get from A to B is going to be not determined by what's going on here on either side of the bottleneck, but what you have to do in order to get through the bottleneck. So think of this as being like a slow step, and this as being a fast step. So what we can say is that the rate, how quickly we get from A to B, depends upon only the slow step and not the fast step. All right, does anybody have any questions so far? All right, let's look at an example here of the kind of thing that you're going to see on the test. So what I'm going to do is I'm going to give you a full chemical reaction for something, as well as the rate equation for that reaction. The rate equation is not based on looking at the reaction. The rate equation would have been found by doing experiments like we talked about last Tuesday. So let's look at the kinds of questions that you need to be able to answer about this. So the first thing is, based on the information, can you say whether the reaction is one step or more than one step, and why that would be? Well, here's the situation. If you've got a rate equation here, it's got K NO to the power of 2. So what we can see is the rate is based on only the NO and not the BR2, because the BR2 is not here. But that's not to say the BR2 isn't reacting. What it means is the rate is depending on the slow step. Remember this bottleneck here. So the BR2 must be reacting in some other step, and that step we know must be faster. So because the BR2 is not part of the rate equation, I can tell you that this is more than a one-step process. Now, what would a one-step process look like? Well, what it would look like is it would involve everything that's in the reactants. And what that would mean is that everything here, the 2 NOs and the BR2, would be reacting in one single step. So the rate equation, if it was one step, would simply involve everything that we see here. You'll notice that the NO is to the power of 2 because of the 2 here in the coefficient. So rate equals K NO squared BR2. That's what it would be if it was one step. But that isn't the rate equation. The rate equation is this, which means it must be more than one step. So I'll stop here for a second. Does anybody have any questions so far?
So if it's more than one step, it's going to be in separate brackets?
If it's more than one step, it won't involve everything that's in the, it won't involve everything that's in the reactants, in the reaction you're given. You'll have things missing. Is that okay, Christina? All right. Does anybody else have any questions?
Wouldn't the exponent 2 be the order?
It is, but in this case, it's related to the is related to the coefficient because we need that many molecules in order to make the reaction go in one step in this case, or that's how many NOs are involved in the slow step. It would be 2. But yes, that is the order. Any other questions?
No, but can we do another example?
We're not done yet, Alexandra. Okay. We have to keep cruising here. This is just the first part. This is the easy part. I'm sorry to say, the hard part's coming up. So does anybody else have any questions about this part here with the A and the B here? Whether it's more than one step, what it would look like if it was one step. So just to give you a little bit more of an idea of what I mean by one step. One step would mean that we've got NO, NO, and Br2, and they're all colliding together at the same time. That would be one step. Instead, we know that what's happening is that in the slow step, we've got 2 NOs. And then the Br2 is happening in some sort of fast step later. So that's what it's really like. This is what it would be if it was one step. Everything would be involved all at the same time. Okay, anybody got any questions? Okay, let's take a look at the next part then. Propose a reaction or set of reactions that fits the data presented in part A. Label reactions as fast or slow. So this is the hard part of doing this. So these are the guidelines that we're going to use in order to come up with these reactions that are involved in these different steps. The first thing is, and this is the most important thing, only the exact reactants in the rate equation may be in the slow step. The reason for that is because the rate only depends on what's in the rate equation. So the rate only depends on whatever you see here, and then the rate is what's going to be in the slow step. And that's what I was talking about earlier with the bottleneck. So the rate is always the slow step's the bottleneck. So these are the only things that are involved in the slow step. The next thing is the reactions you come up with all must add up to give the final reaction. Charges and atoms must balance in each reaction, and the exact same species may not appear on both sides of the same equation. I'm going to wait on explaining that because it's easier to explain once you see the process. So here's how we would solve for this. Now remember what you're given. This is all we're given. We're given this 2NO plus Br2 gives 2NOBr, and we're given the rate equation. That's all we're given. And we're asked to come up with these steps. So there's a couple of things involved here. So I'm going to put some guidelines here, and the guidelines are as follows. All right, so how to tell if slow step is first step. And this is the hardest part, because if you can understand this is just all logic. If you can understand this, then you can sort of understand anything that goes along with this. How to tell if the slow step is the first step. So if the species in the rate equation are in, we'll say all the species. If all the species in the rate equation are in the reactants, the slow step is the first step. So I'm going to try and get you to understand that statement here. All right, so let's first of all see what we're looking at. Let's first of all talk about what the rate equation is. The rate equation is this: rate equals KNO squared. And when I talk about reactants, I'm talking about these guys here, the things that are reacting in the reaction we're given. I'm going to stop there for a second. Does anybody have any problem understanding what I mean by rate equation and what I mean by reactants? Everybody's fine with that, huh? Okay. So let's look what's in the rate equation. What I see in the rate equation is 2 molecules of NO. I look in the reaction, there's 2 molecules of NO. Now, what do I mean by 2 molecules? Well, the NO squared, if there's another way of writing this, rate equals K NO times NO. That's what NO squared would indicate. And I see 2 molecules of NO there. I also see 2 molecules of NO in the reactants here. So that tells me that the slow step must be the first step. If it's not the case, then the slow step is not the first step. And I'll show you an example of that in a bit. So what that means is, and that's why it's important to know this, the slow step is the first step. And this is what I would come up with first. I also know that any reactions I come up with are going to have to add up to the reaction that I'm given, which is this one, the final equation, which is what I was given initially. So that's what I do first. I know that the slow step is going to involve whatever's in the rate equation. I'll say it again. The slow step is going to be determined by whatever's in the rate equation, which is 2 molecules of NO. So NO goes NO plus NO, and that gives me something which I haven't come up with as a slow step. All right, does anybody have any questions so far? Any questions so far? Now, one of the things I like to do is, if I can make the products here from these reactants, then I will. But as you can see, there's no BR involved anywhere here, so I can't make this product. So I'm forced to make something else. So what I can do is I can just shove these things together and make a new compound, which in this case is just going to be N2O2. Now, the thing I make here, it says here that the exact same species may not appear on both sides of the same equation. So what I mean by that, when I'm looking at that, I see I've got N2O2. That's different to these 2 NO molecules. So let me show you what I couldn't do. And you might be wondering why I can't do this. Okay, so that would be the same. If I had NO plus NO gives 2 NO, that's the same thing. NO plus NO is 2 NO, so I can't do that. I can do N2O2. Let's look at the difference between what 2 NO is and what N2O2 is. So NO That's 2NO. Now this is N2O2. I'm hoping you can see the difference between them. N2O2 is joined together as one molecule, whereas two NOs are two separate NO molecules. So N2O2 is different to two NOs. And that's why I couldn't use that as my reaction for the slow step. Anybody have any questions so far?
Can you show that what it says under 4? It says the exact same species may not. Can I just
Oh, sure. Okay. Yeah. Okay. It's the exact same species may not appear on both sides of the same equation.
Okay. So when it says that, it means it may not, it cannot.
Cannot.
You're not allowed to do that.
You can't
Okay.
do it. Yeah. So I can't
Okay.
that's why I can't do two NOs. I can do N2O2 because that's a single molecule that's different to two separate ones. But I can't just say, well, NO plus NO is equal to 2NO because, well, that's the same thing. I'm not changing anything by doing that. Now, one thing you'll notice here is that nowhere in the final equation do you see the N2O2. So what must be happening is the N2O2 that gets formed in the first step must be reacting with Br2 in the second step. And as you can see, magically, that can form our product here, which is two NOBRs. So that balances out. And that step would be fast. So what you'll notice is you've got the N2O2 and you've got the N2O2 down here. So the N2O2 that's formed in the first step is used in the second step to get the product. So it turns out that when you add these together, the N2O2s all cancel out and we're just left with 2NO plus Br2 gives 2NOBr. So these would cancel. Now, I'm not a real fan of putting these lines through because people think, well, that means they've just disappeared. No, I'm just saying that that's what's happened is the N2O2 is formed in the first step, then it's used up in the second step by the Br2. And that would be the final answer that we're looking for. Does anybody have any questions?
So you use the products from the first reaction to form the reactants of the fast one?
Yeah. Because we've got to use the Br2. We haven't used it yet. And we also need to form 2NOBr. So that's why I know to use Br2 down here because in the next step. But whatever I form here must go down in the second step to be used up because it's not appearing in the rate equation. Not appearing in the equation at the end here. All right, any other questions so far?
So it has to be a multi-step for it to include the fast and slow?
That's right.
Okay.
And we know it's multi-step because when we look at the rate equation, it doesn't contain all the reactants. See, in order for it to be one step, it would have to be rate equals K NO squared and the Br2 would have to be in the rate equation as well. But it isn't. So we know that it must be more than one step just based on that. Anybody have any other questions? Okay, let's look at another example. So this one is C3H8 plus Cl2 gives C3H7Cl plus HCl. The rate is equal to K C3H8 and Cl. All right, so let's go back to here. I'm going to erase some of the stuff I've got here. All right, let's look at what I've got here on the page here, how to tell if the slow step is the first step. So if all the species in the rate equation, remember this is the rate equation I'm pointing to here that starts with the word rate. If all the species in the rate equation are in the reactants, the slow step is the first step. So I'm looking at the rate equation. I see C3H8 is a reactant, that's fine. But you'll notice that Cl is not a reactant. Cl2 is, but Cl is not a reactant. Right, that's what I'm asking you to see here. See, Cl is not a reactant. What that tells me is the slow step is not the first step because of that. So let's go back to the previous one. You'll notice in the previous one we had 2 molecules of NO, and there are 2 molecules of NO as a reactant here. But in this instance, we've got Cl, and Cl is not a reactant. So this is what I want you to understand. If Cl is in the rate equation, then you've got to be asking the question, well, where the heck did Cl come from if it's not a reactant? But if you had to ask yourself this question, would you believe the Cl came from the C3H8 or the Cl2? What do you think? Do you think the Cl came from the C3H8 or the Cl2? It's not a trick question.
CL2.
The CL2.
It has to come from the Cl2, right? It can't come from the C3H8. So the thing is, if the Cl is coming from somewhere, it must be coming from a previous step. I'll say it again. If the Cl is in the slow step, it must have come from a previous step. I'll say it one more time. If the Cl is in the slow step, it must have come from a previous step since it's not a reactant. The Cl must have come from the Cl2. So this is what I would come up with first, based on that logic. I would come up with C3H8 plus Cl as being the slow step. And I'll leave a space there for the products. But I also know that there's going to have to be a step before it as well, a step explaining how we get to Cl. And as we said, the Cl is likely to have come from the Cl2. So Cl2 is giving Cl plus Cl. Now I know you're looking at that, you're saying, well, isn't that the same thing? No, it isn't. Because if you look at what Cl2 is, Cl2 would be 2 Cl's joined together, whereas Cl plus Cl is 2 separate Cl's. So we are doing something different here by forming that. So what you're seeing here is the Cl2 is forming the Cl plus the Cl. And then we know in the next step, C3H8 is reacting with one of those Cl's to form a product. Now, as I said earlier, when you're figuring out what product goes here, you want to try and make one of these products down here that you're actually trying to get. So I'm going to leave a space here for another step and put down our final equation here. Now in this instance, I could actually make C3H7Cl, or I could make HCl. So I could go either way with that, but I'm going to go with making the C3H7Cl. So I'll go ahead and do that. So I've already succeeded in making one of these products, which means I don't put the C3H7Cl down here like I did previously on the other one, because I actually needed that as a product. But that reaction isn't balanced. So if you look at it, there's 3 carbons, 3 carbons. We've got 8 hydrogens over here and only 7 on this side. We've got 1 Cl and 1 Cl. So what that tells us is that we've got one other product, and that's the H over here. Does anybody have any questions about how I came up with that H?
Quick question.
Yeah. Mm-hmm.
So what you're saying is in the product that you have the C3H8 plus the Cl, you're basically taking the H and leaving it on its own so that you can still have the H7 plus the H to make the H8, which gives you the item on the very bottom.
Right, that's right, the C3H7Cl. And that was my guideline. I wanted to make that if I possibly could. And I could because I had the ingredients to do it. I couldn't make both though. I couldn't make the HCl as well because I don't have enough Cl.
Okay, so as long as you include that H in there like that, then it balances it out for the
Yes.
bottom.
That's exactly
Okay.
right. Yeah, that's right, Emmeline. Sorry, Caitlin, I don't know. Can you still not hear me, Caitlin? My connection seems okay. Okay, any other questions so far?
So the Cl2 that yields the Cl plus Cl, is that the fast step?
It is a fast step. Yes, it's a faster step than the slow step.
Okay.
But by definition, any step that isn't the slow step is going to be faster. So I actually often don't even put the fast step in here if I've got the slow step because it's assumed that it's fast. But yeah, I should put fast next to it as well. Now you'll notice that we've already accounted for the C3H7Cl, which is fine, but we haven't accounted for the H. So the H goes down here, and you'll notice that there's a Cl we haven't used yet. So H plus Cl gives, what do you know, HCl, and that would be our third step, which is also fast. So you might be asking, well, how do I know the H goes down here? Well, it's not a reactant or a product, so it must be used up in the next step. And you'll notice we had to take account of the second Cl here we formed in the first step as well. So that gets used up in the third step. We get HCl, which means everything now adds up to what we've got down here. So you can see you've got C3H8, we've got Cl2, we've got C3H7, and we've got HCl. Everything ends up down here. I can cancel the things out and that's how we end up with getting all of that for our reactions. Okay, does anybody have any questions? Any questions? Okay, let's look at some examples, and I have plenty of these examples in the folder that's called Rate Equations and Reactions. Now, what I wanted to do here was focus mainly on being able to tell whether the slow step is the first step or not. All right, so let's look at the guideline I've got written down here. Okay, so how to tell if the slow step is the first step. So I want you to look at example A here. For some reason I can't pull up the, I'm trying to pull up the thing here. Won't allow me to enlarge it. There it is. There we go. Okay, so how to tell that the slow step is the first step? If all the species in the rate equation are in the reactants. Now remember what the rate equation is. The rate equation is this one here, and these are the reactants that I'm talking about up here. So I'm looking at it, and the question you're asking yourself is SO2 a reactant? The answer is yes. Is O2 a reactant? The answer is yes. What that would mean is that the slow step is the first step. Now the question you might be having is, well, what about the other SO2? That's also a reactant, but that's not what we're asking here. Let's say it was KSO2 squared O2. Can anybody tell me what that would indicate? If the rate happened to have all of the reactants, the rate equation, what would that mean? Let's say the rate was, it did contain all the reactants. What would it mean?
There's only one step.
It's only one step. That's exactly right. So this is not a one-step process. We can already determine that by looking at the rate equation. But what I know is that the first step is the slow step. I'm going to wait a second for my connection to stabilize here. Okay, I think it's going to be okay now. All right, let's look at B. Is the slow step the first step? What do you all think? I wonder, I might be able to do a poll here. Might not be worth it. Give me a second. Okay, so I've just put up a poll here. Can you see it? Is the slow step the first step? We're talking about B here. Talking about B. Is the slow step the first step? All right, so I have a few people saying yes and a few people saying no. Or more people saying no now. Okay. All right, I'm going to end the poll here. It looks like 19 people say yes, 7 people say no. The answer is actually yes. It is, the slow step is the first step. We're looking at B here. So what I'm saying here is you look at the rate equation if all the species in the rate equation are in the reactants, the slow step is the first step. So I'm looking at the CO. CO is a reactant. S is a reactant. So the slow step is the first step. Let's look at.
So does it not
Go on.
matter?
Go on.
So does it not
Sorry, Alex. You're breaking up here a bit. Could you repeat that, please?
Does it not matter that the 2 is not in the rate equation?
Right. Because if it was, it would mean that it was one step. Look at the language of how we determine the slow step is the first step. If all the species in the rate equation are in the reactants, it's very important you understand that its rate equation are in the reactants, not the other way around. Remember, Alexandra, all poodles are dogs, but not all dogs are poodles.
Dr. Musgrave,
Yeah, Lonnie.
I'm just wondering if there are any exceptions to the rule.
Well, let's continue on, okay? And we'll get a better impression as we go, okay? But don't.
Okay.
I'm going to hold off on that question for a little bit. Let's look at C here. Okay, so I'm going to put up the poll again. Okay, is the slow step the first step? This is for C. All right, so I'm going to wait until we get a fair number of votes here. It's all anonymous, you know, there's no, you don't have to be afraid of voting. Okay. Okay, we got 26 people voted. That's fine. Okay, I'm going to end the poll here. Share the results. So 77% of you said no, 23% of you said yes. The people who said yes were correct. The slow step is the first step. So most of you got that wrong. Now let's see why. Look at the wording. The slow step is the first step. If all the species in the rate equation are in the reactants, the slow step is the first step. So let's look at the rate equation. N2H4 is there. Is that a reactant? Yes. So automatically we know that the slow step is the first step. Now you're saying, well, what about the O2? Well, if the O2 was in the rate equation, it would only have been one step. But look at the wording. If all the species in the rate equation are in the reactants, the slow step is the first step, not the other way around. Remember, all poodles are dogs, but not all dogs are poodles. Just because it goes in one direction doesn't mean it goes in the other. Does anybody have any questions about that one? All right,
aren't those both considered reactants though?
They are,
Since
but
they're on the first side of the
they are.
equation.
They are, but look at look at the wording of the thing here. It says all species in the rate equation. This is the rate equation, and N2H4 is in the rate equation. Is in the reactants. So is N2H4 a reactant? That's the only question we're asking. And if it is, then the slow step is the first step. That's all we're asking. Is this a reactant? Is that okay, Emmeline?
Okay, so what you're saying is the N2H4 is the reactant, and that's really what you're looking for is the first part of that?
Well,
Not two?
you're just looking to see if whatever's in the rate equation is a reactant. All right, let's skip to E. Right, let's look at E.
So if
Hang on, give it a second here. Let it stabilize. Okay, somebody had a question. Looks like we're okay now. Somebody was going to ask a question. Okay, let's skip to E. Let's stop sharing now. Okay, so this is E that we're looking at. Is the slow step the first step? Okay, I'll give you another few seconds. Is the slow step the first step in E? Okay. I'm going to go ahead and end the poll here. This is what we come up with. So 15 people said yes, 11 people said no. The answer is no. The slow step is not the first step. Oh, wonder why that is. Okay, let's read this again. If all the species in the rate equation are in the reactants, the slow step is the first step. I mean, look at this. I look at N2O. Is N2O a reactant? Yes, it is. Is O a reactant? It isn't. O is not a reactant. O3 is a reactant, but O isn't. Not O by itself. So the slow step is the second step. Well, what's the implication here? Well, the O must have come from somewhere. I'll say it again. The O must have come from somewhere. I'll say it again. The O must have come from somewhere. It didn't come from it isn't a reactant, so it must have been made. Where was it made from? Well, it was probably made from the O3. Any questions? All right, let's look at F. Okay, F. Slow step, first step. Okay, another few seconds here. Is the slow step the first step? The answer is yes. So most of you got that right. So you're looking here, CaClO2, yes, that is a reactant. Mg, that's a reactant, yes. See, everything is in the reactant, so nothing has to come from anywhere else. So the slow step is the first step. Now take a look at G.
So
Sorry, go on. Oliver?
okay, so the coefficient in front of the mg, that doesn't matter.
No, because if it was mg squared, it'd be only one step anyway, which means this wouldn't even be a discussion. What we're trying to determine here is if something in the slow step has to be made from something else. Take a look at G. Take a look at G. All right, G, slow step, first step. More of you are getting the idea now. It's good. I can see the results come through here. Give you another couple of seconds here. Make a decision. Those 4 of you haven't voted. Okay, I'm going to end it here. So is the slow step the first step? The answer is no. The reason is because yes, C6H6 is a reactant, Br plus is not a reactant. What do you think the Br plus was made from? Does anybody want to guess where the Br plus came from? Any thoughts? Any thoughts where that Br plus is coming from? Anybody want to guess? So say again.
The first reaction, that's going to be before the slow reaction.
Yes, but what would the Br plus have been made from? C6H6 or Br2?
BR2.
Yeah, that's right. So the Br plus came from the Br2. That's what I know. Okay.
So if we actually had to solve that, how would we find BR plus?
Oh, we'll get to that in a second. I'm just one step at a time here. One step at a time. We have to get this whole slow step, first step business out the way. We'll get to that in a second. All right, let's look at H. Slow step, first step. H. Okay, another couple of seconds. Okay, I'm going to end it now. So for H, the slow step is the first step. You're asking yourself, is C5H6NBr3 a reactant? It is, and that's all that's necessary. You see, it doesn't have to be made from anything. The reactants are already there. So it doesn't have to be, there's no way that this has to have the slow step as the second step. Slow step must be the first step because you can make it from the reactants that you have. That's what I'm trying to say. Okay. All right, what about I? First step, slow step. Let me pull up the new poll here. Okay. I. First step, slow step. Yes or no? And more of you are getting it now, which is good. Okay, I'm going to end the poll here. There you go. And the answer is yes. Is N2O a reactant? Yes, it is. Is O2 a reactant? Yes, it is. So the N2O doesn't have to be made from anything. It can be pulled from the reactants. The O2 is just a reactant as well. Okay. All right, what about J? Slow step, first step. Is the slow step the first step? Yay, now we're getting more. Okay, this is good. Come on, a little bit more. Okay, we'll end the poll here. What do you know? And the answer is no. See, look, C2H4, that's a reactant. I plus is not a reactant. Where did the I plus come from? It had to come from the I2. This is why this must not be the first step. Any questions?
So if it's like a one-step equation, is that going to be a fast or slow reaction, or does that not come into play?
It wouldn't come into play because it's only one step.
Okay.
You know, there would be no slow step, there would be no fast step, it's just one step. But I know that it can't be one step because not everything in the reactants is in the rate equation. That tells me it must be more than one step. Then we've got to determine, well, if it's not one step, is a slow step the first step or the second step? And that's what we're trying to figure out here. Okay, I do have some more of these, and I'm not going to do all of them, but we'll do a couple more here. Okay, let's look at, yeah, I think I like number one. Let's see, number one. Number one, first step, slow step. It's interesting, isn't it? Put in your best guess, folks. Number one, slow step, first step. Okay. The answer is no. A fair number of you said yes. Now I know why you said yes, but let's talk about this a little bit. Look at the rate equation, FeOC. The only question you've got to ask yourself is FeOC a reactant? And the answer is no. FeOC is not a reactant. Can you make FeOC from the reactants? Yes, but that's the entire point. That must mean that FeOC is in a second step because it has to have been made from these reactants. So the slow step must be the second step. Any questions? Number two, slow step, first step. Number two, slow step, first step.
Could you make those a little bit bigger?
Oh, sure. Yeah, I can do that. Okay. Is that better? Slow step, first step, number two. Okay. Last votes, come on. So number two, the slow step is the first step because C is a reactant and there are two SO2s here. So yes, that one is the slow step is the first step.
Question.
Yeah.
So you said it is a slow step because there are two SO2s that the way it's written is okay for it to be that way.
That's right.
So the number does come into play only at that time.
Well, the only question, Emmeline, I think you're asking the wrong question. What you've got to be doing is looking at the rate equation, just asking, is C a reactant? Are there two SO2s in the reactants? That's all you're asking.
Okay.
That's all you're asking.
If it had just said C and then SO2, wouldn't the answer still be yes?
Yes, Caitlin. Yes, you are completely correct. If it was just C and SO2 by itself here, yes, the answer would still be yes. What if it was C and SO? What would you say then?
No.
No, because our SO is not a reactant. I think I'm beginning to see some understanding here. This is good. This is good. All right. What about number 8? That's good. Okay. Number 8. Number 8. Is the slow step the first step? Number 8. Is the slow step the first step? That's okay. Number 8. Slow step, first step. And the poll, share the results. The answer is no. Look, CO is not a reactant. And you all got that. CO is not a reactant. But we know it can be made from C plus O2, but that's the whole point. CO is not a reactant. The slow step must be the second step. All right, what about number 10? Number 10, slow step, first step. Number 10, slow step, first step. The answer is no. H2O2 is not a reactant. H2 and O2 are reactants. We can make H2O2 from H2 and O2, but H2O2 itself is not a reactant. The answer is no. So the slow step is not the first step. All right. Okay, let's try 13. Number 13. 13. Slow step, first step. 13. Ah, yes. Yes. All right. All right. I think it's finally beginning to twig. Look at that. Look at that. The answer is yes. Is N2O a reactant? Yes, it is. Yeah, it's a beautiful thing. All right. So at least we're getting closer here. All right. It's good. Let's go back to the problem set that I had over here. Okay. We'll do an example here for now. This does have answers, by the way, and you can see them there. And you have access to this too. But let's look at we'll look at A to begin with and how we would handle it. All right, so A. So we know that the slow step is the first step because SO2 and O2 are both reactants. So what I would do is I do SO2 plus O2 gives something. and that's slow. And then I know everything's going to add up to 2SO2 plus O2 gives 2SO3. Now I can make SO3 here as a product of the first step. Can anybody tell me what I'd have to do to balance it? What's missing?
An oxygen.
One oxygen by itself, right? There we go. So that oxygen by itself plus the other SO2, remember it's 2 SO2s down here, would make magically the other SO3, and that would be it. So that's the fast step. So you might be wondering where to pull the other SO2 from. Well, remember I know I need to use 2 SO2s. I've already used the O2. You see the O's cancel here. And that would leave me with my reaction. Anybody got any questions about the first one? Okay. Okay, Emmeline, you had asked me about number. Let's look at G. All right, this one's a hard one, number G. So what we talked about with number G is that the slow step is not the first step. It must be the second step, because Br plus had to come from somewhere. Well, let's look at where the Br plus came from first then. The Br plus would have had to have come from the Br2. Okay. So Br2 is giving Br plus. How do I balance that? What do I have to add to balance that?
Another BR.
Well, another Br, but that's not completely balanced. That's not completely balanced.
A BR minus?
Br minus. Yeah, that's a bit tricky, isn't it? See, this has to be balanced not only for atoms, but for charge as well. So plus minus, that gives the neutral over here. So plus and minus is 0. Br2 is 0 as well. So this has to add up to C6H6 plus Br2 gives C6H5Br plus HBr. And I can make the C6H5Br how do I balance it? What's missing? Anybody tell me what's missing?
An H.
Not just an H. Again, we're having an issue with balancing here because this is C6H6 plus Br plus. What does that have to be? What has to be H plus? And then H plus plus Br minus gives HBr. And that would finish it up. So this is fast and the other one's fast as well. All right, don't panic, folks. We'll do some more examples of these when we come back on Thursday. And then I'll show you what the ones on the test look like as well. So we'll leave it there for today. And I'll talk to you later. Yes, that one tricky, LOL. Yes, you're right. You're right, Oliver. But it's mainly the charges that makes that one tricky. All right, we'll leave it there for today. Thanks for coming. I'll see you all on Thursday.
Thank you, Professor.
Thank you.
Professor.
No worries. Thank you. Thank you. All right. See you all later.
Hey, sorry. Can you hear me all right?
I can hear you, Alexi. What's up?
I just wanted to explain why I had my camera off. So my girlfriend is usually sleeping when I start my class, and she has to get ready for work, and my computer's in our room. So I just, for some of the class,
All right, that's okay. Thanks. I appreciate the explanation, Alexi. Thank you.
yeah, I just didn't want to be like turning that on and off. And
All right, no worries.
right
I
on.
appreciate.
Have a good one.
I appreciate it. Thanks, Alexi. Bye bye.
Bye bye.